Welcome to Calming Cosmos. I'm so glad you're here with us tonight. Find yourself a comfortable position wherever you are right now. Let your body sink into the softness beneath you, feeling supported, feeling safe. There's nowhere else you need to be, nothing else you need to do. This time, this moment is just for you. If you'd like, you can gently close your eyes. Take a slow, deep breath in, filling your lungs completely, and let it go. Another breath, feeling your shoulders drop away from your ears, your jaw relax, your whole body becoming heavy and peaceful. With each breath, you're releasing the day, letting go of any thoughts or worries, allowing yourself to simply be. Tonight, we're going on a journey together, a gentle drift through our solar system, visiting each of the 8 planets that circle our sun. We'll float peacefully past Mercury, the tiny world closest to our star. Glide through the thick clouds of Venus. Look back at our beautiful Earth, hanging in the darkness, and venture out past Mars to the giant worlds of the outer solar system. We'll marvel at Jupiter, the king of planets, with its great red spot and family of fascinating moons. We'll admire Saturn's magnificent rings, those impossibly thin bands of ice circling the golden planet. We'll encounter Uranus, tipped on its side, and Neptune, the deep blue world at the edge of our planetary neighborhood. There's no pressure to stay awake for this entire journey. In fact, if you drift off to sleep along the way, that's perfectly wonderful. That's exactly what this is for. Let the words wash over you like gentle waves, carrying you deeper and deeper into rest. There's no test at the end, no need to remember anything. Just let yourself float peacefully through space. The journey we're about to take is gentle, unhurried. There are no deadlines here, no schedules to keep. Time moves differently when we're drifting through space. Minutes, hours, they blur together into something soft and peaceful. Your body knows what to do. It's been practicing sleep since before you were born, since you were safe in the womb, rocking gently in the darkness. Take another breath now. Feel how your chest rises and falls, how the air moves in and out. This simple act, breathing, connects you to everything. The oxygen you're breathing was created by stars, by plants, by the ancient ocean. Each breath is a gift from the universe itself. Tonight, as we visit each planet, you might find your mind wandering. That's perfectly natural, perfectly welcome. If you drift away from the words, into your own thoughts, into dreams, that's exactly where you should be. These words are just a gentle current, carrying you towards sleep. You don't need to follow every one, just let them wash over you, soft as starlight, quiet as the void between worlds. So take one more deep breath And let's begin, floating out into the darkness, where our story starts with a star. Our star, the sun. Our journey begins at the very heart of our solar system, with the sun. Picture yourself floating in the vast darkness of space, and there before you, perhaps a safe distance away, is the most magnificent sphere of light you've ever seen, the sun, our star, glowing with an intensity that has warmed our world for billions of years. The sun is immense, truly immense. If you could somehow hollow it out, you could fit 1,300,000 Earths inside. 1,300,000. Let that number drift through your mind, feeling just how small we are, how vast our star truly is. And yet, despite its size, the sun is just one star among hundreds of billions in our galaxy. And our galaxy is just one among hundreds of billions of galaxies. We are so small, and that's okay. That's beautiful. 4.6 billion years ago, in a quiet corner of our Milky Way galaxy, there was a cloud, a giant molecular cloud, floating peacefully through space. This cloud was vast, stretching for light years, composed mostly of hydrogen, the simplest element in the universe, along with helium and traces of heavier elements left behind by stars that had lived and died long before. This cloud was cold, perhaps just 10 degrees above absolute zero, and dark. No stars shone within it. It simply drifted, slowly rotating, slowly evolving for millions of years. And then something happened. Perhaps a nearby star exploded in a supernova, sending shockwaves rippling through space. Perhaps the cloud simply grew too large, too heavy to support itself against its own gravity. Whatever the cause, the cloud began to collapse, slowly at first, almost imperceptibly. The particles of gas and dust began falling toward the center. As they fell, they began to spin, like water circling a drain. The cloud flattened into a disk, rotating faster and faster as it contracted, and at the very center, where most of the material was concentrating, the pressure began to build. The center grew denser, hotter, more compressed with each passing millennium. Imagine millions of years passing, the cloud slowly collapsing, the center heating up. 1,000 degrees, 10,000 degrees, 100,000 degrees. The hydrogen atoms at the core moved faster and faster, colliding with tremendous energy. But still, the temperature climbed. After perhaps 10 million years of collapse, the core reached a critical threshold, 15 million degrees Celsius. At this incredible temperature, this unimaginable heat, hydrogen atoms began to fuse together. Two hydrogen nuclei, normally repelling each other, due to their positive charges, were forced together by the extreme pressure, combining to eventually form helium, and in the process, releasing enormous amounts of energy. The Sun was born. For 4.6 billion years now, our Sun has been fusing hydrogen into helium at its core. Every single second, it converts 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, that mass, is converted directly into energy according to Einstein's famous equation. 4 million tons every second, transformed into pure energy. This energy, this light, is what makes everything possible on Earth. The surface of the Sun, the photosphere, the part we see when we look up on a clear day, glows at about 10,000 degrees Fahrenheit. That's hot enough to vaporize any known material instantly. But this surface temperature, as extreme as it is actually cool compared to the core. Deep inside, at the very heart of the Sun, temperatures reach 27 million degrees Fahrenheit. 27 million degrees. It's almost impossible to comprehend. The light generated in the core takes a long time to reach us. A photon of light created by fusion at the core doesn't simply shoot straight out. Instead, it bounces around, absorbed and re-emitted by atoms countless times, zigzagging through the dense solar interior. This random walk through the Sun can take tens of thousands of years, perhaps even 1,000,000 years, before that photon finally reaches the surface. And then, it takes just 8 minutes to travel the 93 million miles to Earth. When you feel sunlight on your face, you're feeling energy that began its journey in the Sun's core potentially millions of years ago, but completed its journey from the Sun's surface just 8 minutes earlier. Isn't that remarkable? The sunlight warming Earth today began its creation long before humans existed, slowly working its way outward through countless interactions, finally reaching us at this very moment. Think about that for a moment. The warmth you feel on a summer afternoon began its journey before humans learned to make fire, before we discovered agriculture, before we built cities or wrote stories or gazed through telescopes at the very star that created that warmth. The Sun is patient. Its light travels for years through its own substance, then crosses space in minutes, finally reaching your skin, completing a journey that began longer ago than civilization itself. And the Sun is always there, even at night, when your part of Earth has rotated away. The Sun continues shining, illuminating the other side of the planet. Somewhere, right now, someone is watching sunrise. Somewhere else, sunset. The cycle continues, as it has for billions of years, as it will for billions more. Ancient peoples worshipped the sun, not because they were primitive, but because they understood something fundamental. Without the sun, nothing exists. No warmth, no light, no plants, no food, no life. The sun is the source of everything we are. Every calorie of energy you've ever consumed, trace back far enough, came from sunlight captured by plants. You are solar powered. We all are. The sun asks nothing in return. It simply shines, day after day, year after year. Fusion reactions at its core produce energy that eventually becomes the world you know. The blue sky, the green leaves, the food on your table, the thoughts in your mind, all of it powered by a star, our star, the sun. And the sun is not alone. There are hundreds of billions of stars in our galaxy, each one potentially surrounded by planets, each one shining into the darkness, each one a sun for its own worlds. We live in a galaxy of suns, a universe of light, and yet here, on Earth, we are blessed by this particular star, this gentle, steady, patient star that has made everything possible. The sun's surface, if you could observe it closely, is not calm and steady. It roils and churns, constantly in motion. The photosphere shows a granulated pattern, like a field of cells, where hot plasma rises from below, cools slightly, and sinks back down. Each of these granules is about 1,000 miles across, larger than Texas, and they constantly form and dissolve, typically lasting about 8 to 20 minutes before being replaced. Dark spots appear on the surface, sunspots, regions where intense magnetic fields break through, temporarily cooling those areas to about 6,500 degrees. Still incredibly hot, but cool enough compared to their surroundings that they appear dark. These sunspots can be enormous, some larger than Earth itself, and they often appear in pairs or groups, connected by loops of magnetic field. The sun's magnetic field is complex and ever-changing, generated by the churning motion of plasma in the sun's interior. These magnetic fields can become twisted and tangled. Sometimes they grow so stressed that they snap, releasing energy in sudden outbursts. When magnetic fields reconnect violently, the sun releases a solar flare. These are tremendous explosions, releasing as much energy as billions of nuclear bombs in just minutes. Flares emit radiation across the electromagnetic spectrum, from radio waves to X-rays, and they can accelerate particles to nearly the speed of light. When these flares are directed toward Earth, they can create beautiful auroras, but they can also disrupt satellites and communication systems. Sometimes, the sun releases an even larger burst, a coronal mass ejection, where billions of tons of plasma are hurled into space at millions of miles per hour. These massive clouds of charged particles carry embedded magnetic fields, and when they strike Earth's magnetosphere, they can create geomagnetic storms, making the auroras visible far from the poles, painting the night sky with shimmering curtains of green, red, and purple light. The sun also breathes out a constant wind, the solar wind, a stream of charged particles, mostly protons and electrons, flowing away from the sun's surface in all directions. This wind is always blowing, sometimes gently, sometimes fiercely, washing over all the planets. It blows past Mercury at several hundred miles per second, past Venus and Earth and Mars, continuing all the way to the edge of the solar system, where it finally meets the interstellar medium, the space between stars. Our sun is remarkably average in a galaxy of hundreds of billions of stars. Our sun is neither the largest nor the smallest, neither the hottest nor the coolest. Astronomers classify it as a G-type main sequence star, a yellow dwarf, doing what most stars do, converting hydrogen to helium, shining steadily. For billions of years, there are stars much larger than our sun, blue supergiants hundreds of times wider, so hot they shine blue-white. There are stars much smaller, red dwarfs barely a tenth the sun's mass, so cool they glow deep red. Some stars come in pairs, orbiting each other. Some stars pulse regularly, expanding and contracting. Some explode catastrophically at the end of their lives. But our sun is perfectly suited for us. Its steady, reliable output of energy, its position in a stable part of the galaxy, its solitary nature. All of these factors have allowed Earth to develop and maintain life for billions of years. A hotter star would have made Earth too warm, a cooler star too cold. A binary star system might have made planetary orbits unstable. We are remarkably fortunate. The sun will continue shining much as it does now for another 5 billion years. Slowly, very slowly. It's getting brighter as helium accumulates in the core and fusion rates increase. But for billions of years to come, the changes will be gradual, imperceptible on human timescales. Eventually, in about 5 billion years, the hydrogen at the core will be exhausted. When that happens, the sun will begin to change dramatically. It will swell, expanding into a red giant, growing so large it will swallow the inner planets. Mercury will be consumed, Venus too. Earth, our beautiful Earth, may or may not survive. But if it does, it will be scorched, lifeless, far too close to the bloated star. But that's so far in the future, so unimaginably distant, that we need not worry. For now, for our entire existence as a species, For countless generations to come, the Sun will continue its steady work, fusing hydrogen, releasing light and warmth, holding the planets in their orbits, making everything possible. Let's drift closer now, inward from the Sun, to the first planet in our solar system, the small world, the scorched world, the ancient cratered surface of Mercury. We're approaching the innermost planet now, Mercury, named after the swift messenger of the Roman gods. And swift it is, racing around the Sun faster than any other planet, completing an orbit in just 88 Earth days. Mercury is small, so small. If you held Earth in one hand, Mercury would fit in your palm, about the size of our moon. It measures just 3,000 miles across, the smallest of the 8 planets. You could fit about 18 Mercuries side by side to equal Earth's diameter. But don't let its size fool you. Mercury is dense, incredibly dense. While Earth's core makes up about 30% of our planet's volume, Mercury's core makes up a staggering 60%, a massive ball of iron and nickel, packed tight beneath a relatively thin, rocky crust. Scientists believe Mercury might have once been larger, but a massive impact early in its history blasted away much of the lighter rocky material, leaving behind the dense metallic core. If you could somehow stand on Mercury's surface, you would feel gravity pulling you down, but only about 38% as strongly as on Earth. You could jump 3 times higher, though you'd still land firmly. The small world still has enough mass to hold you to its surface. As we drift closer, maintaining a safe distance from the intense heat, the first thing you notice is the temperature. Mercury orbits just 36 million miles from the Sun. Earth orbits 93 million miles away, so Mercury is less than half our distance, close enough that the Sun would appear 3 times larger in Mercury's sky than it does in ours, the day side, the side facing the Sun. Bakes at 800 degrees Fahrenheit, 800 degrees, hot enough to melt lead, hot enough to melt zinc and tin. The rocks themselves would glow dull red if you watched them in the dark, radiating heat back into space. But turn to the night side, the dark side facing away from the Sun, and everything changes. With virtually no atmosphere to hold the heat, to transport warmth around the planet, the temperature plummets, minus 290 degrees Fahrenheit, nearly 300 degrees below zero, cold enough to freeze carbon dioxide solid. This is the most extreme temperature range in the entire solar system. 800 degrees on one side, minus 290 on the other, a swing of more than 1,000 degrees between day and night. Nowhere else experiences such extremes. Why does Mercury have virtually no atmosphere? It's so close to the Sun that any gases are either blown away by the solar wind or escape due to the planet's weak gravity. A few stray atoms exist: hydrogen, helium, oxygen, sodium, trace amounts captured from the solar wind or released from the rocks, but nothing you could call an atmosphere. The pressure at Mercury's surface is less than 1/1,000,000th of Earth's atmospheric pressure. Without an atmosphere, the sky would always be black, even during the day. With the sun blazing overhead, the sky would remain dark. Stars would be visible all around the sun, twinkling in the airless void. No blue sky, no clouds, no weather, just the eternal darkness of space, punctuated by the brilliant sun. The surface below us is ancient, heavily cratered, looking much like our moon. Billions of years ago, in the early days of the solar system, when planets were still forming, rocks and debris orbited everywhere. These planetesimals, ranging from dust grains to mountain-sized boulders, crashed into planets constantly. Each impact left a scar, a crater. Mercury's surface is covered with these craters, ranging from tiny pockmarks just a few feet across to enormous impact basins hundreds of miles wide. The largest of these, the Uranus Basin, stretches 950 miles in diameter. When the asteroid that created Galilean struck Mercury, the impact was catastrophic. The energy released was equivalent to trillions of nuclear bombs. The explosion excavated a huge basin, threw up mountain ranges around its rim, and sent shockwaves through the entire planet. On the exact opposite side of Mercury from Uranus Basin, the ground is strange, chaotic, jumbled. Scientists believe the seismic waves from the Galilean impact traveled through the planet, focused on the opposite point, and disrupted the surface there. Even billions of years later, you can see the effects of that tremendous collision. Between the craters, the surface shows other features. Long cliffs, called scarps, stretch for hundreds of miles. These formed as Mercury cooled and shrank. The iron core contracted as it solidified, causing the entire planet to shrink slightly, and the crust wrinkled and folded like the skin of a drying apple. Some of these scarps rise more than a mile high, creating cliffs that would dwarf anything on Earth. Mercury rotates, but very slowly. It takes 59 Earth days to complete one rotation on its axis. But remember, it orbits the Sun in just 88 days. This creates a peculiar relationship. Mercury is locked in what astronomers call a 3-to-2 resonance. It rotates exactly 3 times for every 2 orbits around the Sun. This creates the strangest day. If you stood on Mercury's surface, a single day from sunrise to sunrise would last 176 Earth days, nearly 6 Earth months. The Sun would rise slowly in the east, spend 88 days crawling across the sky, set slowly in the west, and then darkness would reign for 88 more days before the Sun rose again. And during that long day, the Sun would do something even stranger. At certain latitudes, it would appear to stop in the sky, move backward, then resume its forward motion. This happens because Mercury's elliptical orbit causes it to speed up and slow down. And at certain points, the change in orbital speed overtakes the rotational motion, making the Sun appear to reverse course briefly. For a long time, scientists thought Mercury was utterly dead and dry, a scorched, airless rock with nothing interesting except craters. But in the 1990s, radar observations from Earth revealed something shocking. At Mercury's north and south poles, in craters where sunlight never reaches, there appeared to be ice, water ice, on one of the hottest planets in the solar system. How could this be? These polar craters lie in permanent shadow. Their floors never see direct sunlight. In these eternal shadows, temperatures stay below -300 degrees Fahrenheit, cold enough for water ice to survive for billions of years. The ice probably came from comets that struck Mercury long ago. When the comets vaporized in the heat, some of the water found its way to these polar craters, and there it remains, frozen, preserved in the only places on Mercury cold enough to hold it. NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed the ice. The spacecraft also discovered that the ice is likely covered with a dark layer of organic material, complex carbon compounds, perhaps also delivered by comets. Even on this scorched world, the building blocks of organic chemistry and water found refuge. These polar craters on Mercury are among the most alien environments in our solar system. Imagine standing at the rim of one of these craters. Behind you, the sun blazes with terrible intensity. The rocks beneath your feet radiate heat like a furnace. But when you look down into the crater, into that permanent shadow, you see darkness so complete, so absolute, that no sunlight has touched it for billions of years. In that darkness, temperatures plunge to levels colder than liquid nitrogen. Ice that has been there since the solar system was young, since dinosaurs walked on Earth, since the first single-celled organisms appeared in our oceans. That ice has waited, frozen, unchanging, while entire species rose and fell on distant Earth, while continents moved, while mountains grew and eroded away. And in that ice, there might be organic molecules, the building blocks of life, complex carbon compounds delivered by ancient comets, preserved in the cold, waiting. Mercury, the scorched planet, the burned world, holds frozen water and organic chemistry in its darkest corners. It reminds us that the universe is full of contradictions, that even in the most extreme places, the most inhospitable, there are pockets of stability, places where the unexpected can hide. Mercury has witnessed so much. It was there when the sun was young and violent, when the solar system was full of debris, when massive collisions were common. Every crater on its surface tells a story of impact, of catastrophe. But Mercury endured. It remains, small but resilient, battered but unbroken, orbiting faithfully, racing around the sun, the eternal messenger. Mercury has no moons, no rings, nothing to keep it company as it races around the sun. It's alone in its swift orbit, the ancient messenger, its cratered surface baking and freezing, unchanged for billions of years, a world of extremes at the doorstep of our star. Let's move outward now, leaving Mercury behind, drifting to the second planet, the veiled world, shrouded in clouds so thick they hide the entire surface. Venus, named for the Roman goddess of beauty, but concealing hellish conditions beneath her brilliant clouds. Venus, the morning star, the evening star, the brightest object in our sky besides the sun and moon. From Earth, Venus appears as a brilliant point of light, so bright it can cast shadows on a dark night, so beautiful it has inspired poets and lovers throughout human history. Ancient cultures worshipped it, named it after their gods. For thousands of years, humans gazed at Venus and imagined it must be a paradise world, perhaps a tropical jungle, perhaps an ocean world, perhaps even a sister to Earth. But as we approach, as we draw near to this cloud-wrapped world, we begin to understand the truth. Venus is not paradise. Venus is hell. The planet appears before us, almost exactly Earth's size, just 650 miles smaller in diameter, nearly the same mass, nearly the same density, born from the same disk of gas and dust that formed all the planets. Venus and Earth are twins, siblings, and yet they could hardly be more different. The first thing you notice, even from a distance, are the clouds, thick, impenetrable, yellow, white, completely obscuring the surface. These aren't fluffy water clouds like on Earth. They're clouds of sulfuric acid, the same chemical used in car batteries, droplets of acid suspended in the atmosphere, forming a dense blanket that extends from about 30 to 40 miles above the surface. These acid clouds are caught in fierce winds. The upper atmosphere races around the planet at over 200 miles per hour, circling Venus in just 4 days, even though the planet itself barely rotates. This super rotation, this screaming wind, is driven by solar heating and complex atmospheric dynamics that scientists are still working to fully understand. Venus itself rotates, but so slowly it almost seems frozen. One complete rotation takes 243 Earth days, 8 months, slower than any other planet. And stranger still, Venus rotates backward, retrograde, opposite to nearly everything else in the solar system. If you could somehow see through the clouds and stand on the surface, you would see the sun rise in the west and set in the east. No one knows for certain why Venus spins backward. Perhaps a massive collision early in its history knocked it askew, flipping its rotation. Perhaps gravitational interactions with the sun over billions of years gradually reversed its spin. The answer remains a mystery, but the real horror of Venus, the real nightmare, lies at the surface. As we descend through those sulfuric acid clouds, the atmospheric pressure begins to build. On Earth, we live at the bottom of an ocean of air that presses down with about 15 pounds per square inch. Comfortable, barely noticeable. On Venus, the pressure at the surface is 92 times greater. 92 atmospheres, like being 3,000 feet deep in Earth's oceans. The pressure would crush a human body instantly. Even heavily armored spacecraft can barely withstand it. Soviet Venera landers, built like deep-sea submersibles, lasted only an hour or two on the surface before being destroyed. And the temperature is even worse. At the surface, Venus reaches 870 degrees Fahrenheit, 870 degrees, hot enough to melt lead, hot enough to melt zinc and tin, hotter than Mercury, despite being nearly twice as far from the Sun. Venus is the hottest planet in the solar system, not because of its distance from the Sun, but because of the greenhouse effect, run completely out of control. Venus's atmosphere is 96% carbon dioxide, a thick blanket of this greenhouse gas, trapping heat with ruthless efficiency. Sunlight filters through the clouds, reaches the surface, warms the rocks. The rocks try to radiate heat back to space as infrared radiation, but the carbon dioxide absorbs this heat, traps it, reflects it back down, again and again, until the entire planet is an oven, a furnace, day and night without relief. The clouds contribute too. They reflect about 75% of incoming sunlight back to space, which is why Venus appears so bright from Earth. But the sunlight that does make it through gets trapped, unable to escape, cooking the surface relentlessly. Beneath these hellish conditions, beneath the crushing pressure and searing heat, the landscape is surprisingly varied. Venus has mountains, valleys, vast plains of volcanic rock. The surface has been mapped by radar from orbiting spacecraft, revealing a complex world hidden beneath the clouds. There are two continent-sized highlands, Ishtar Terra in the north, about the size of Australia, and Aphrodite Terra near the equator, larger than Africa. These highlands rise miles above the surrounding plains, dominating the landscape like Earth's continents. Maxwell Montes, the highest mountain on Venus, towers 7 miles above the mean surface level, taller than Mount Everest. Its slopes show a mysterious bright material in radar images, possibly metallic compounds that sublimate from the rocks at lower elevations and condense at the cooler heights. Venus is geologically young. The surface is only about 500 million years old, suggesting that volcanic activity has resurfaced the entire planet relatively recently in geological terms. Some scientists believe Venus undergoes catastrophic global resurfacing events every few 100 million years, where the entire crust melts and reforms, releasing vast amounts of volcanic material, creating the surface we see today. Thousands of volcanoes dot the surface. Shield volcanoes, similar to those in Hawaii but much larger. Dome volcanoes, volcanic flows stretching for hundreds of miles. Most are probably extinct now, but some may still be active. Recent observations have detected fluctuations in sulfur dioxide levels in the atmosphere, possible evidence that volcanoes continue to erupt even today, adding to the hellish conditions. There are also features found nowhere else. Coronae, circular structures hundreds of miles across, where hot plumes of magma pushed up from below, bulging the crust before collapsing back down, creating concentric rings of ridges and troughs. Arachnoids, spiderweb-like patterns of fractures spreading across the plains. Pancake domes, perfectly circular, flat-topped volcanic constructs where thick lava oozed out and spread before solidifying. Long ago, perhaps Venus was different. Some scientists believe Venus once had oceans, liquid water covering much or part of its surface, with a climate perhaps not unlike early Earth. Warm, wet, with clouds of water vapor instead of sulfuric acid. But Venus orbits closer to the Sun, 37 million miles closer than Earth. It receives nearly twice the solar radiation, and as the Sun gradually brightened over billions of years, as it does naturally as hydrogen is consumed, Venus grew warmer. The oceans began to evaporate. Water vapor, itself a greenhouse gas, trapped more heat, which caused more evaporation. In an accelerating feedback loop, a runaway greenhouse effect. Eventually, all the water evaporated. Ultraviolet light from the sun broke apart the water molecules. Hydrogen, being light, escaped to space. Oxygen reacted with the rocks, oxidizing the surface. And the oceans, the beautiful oceans, were gone forever. Without liquid water to dissolve carbon dioxide and lock it into rocks, as happens continuously on Earth through the carbonate-silicate cycle, all of Venus's carbon dioxide remained in the atmosphere, building and building, creating the crushing, boiling greenhouse world we see today. Venus is a warning, a cautionary tale. A planet so similar to Earth in size and composition that took a different path. It reminds us how precious our world is, how how delicate the balance, how easily things could have gone differently. Venus and Earth, born together, evolved apart. One became a paradise for life, the other a vision of hell. Think about the path not taken. Earth could have been Venus. If we'd formed just a little closer to the sun, if our oceans had evaporated, if the greenhouse effect had spiraled out of control, we might have ended up just like our sister world, a toxic atmosphere. Surface hot enough to melt metal, oceans turned to vapor and lost to space forever. But we didn't. Some combination of distance, of size, of timing allowed Earth to keep its water, to develop plate tectonics that cycle carbon dioxide into rocks, to maintain a stable climate over billions of years. We got lucky, remarkably, improbably lucky. And Venus reminds us that this luck isn't permanent. Earth's climate is a delicate balance. Systems that took billions of years to establish can be disrupted. The greenhouse effect that turned Venus into hell works the same way on Earth. Carbon dioxide traps heat. Add more, and temperatures rise. The difference is one of degree, of balance, of feedback loops that can either stabilize or spiral out of control. Venus had rivers once, perhaps rainfall, perhaps clouds of water vapor instead of sulfuric acid. It might have been a beautiful place, a warm ocean world. Perhaps life even emerged there. Simple microbes in those ancient seas, living briefly before the runaway greenhouse destroyed everything. We'll never know. Any evidence is long gone, erased by the heat, by volcanic resurfacing, by billions of years of harsh conditions. If Venus once harbored life, it took that secret to its grave. Now only the hellscape remains, a cautionary tale written in the sky. But there is beauty even in this cautionary tale. Venus reminds us that planets are dynamic, that conditions change, that nothing is permanent, and that makes our current Earth, our living Earth, our breathing Earth, all the more precious. We live in a moment of stability, a window of habitability, and that window won't last forever. Appreciate it while you can. This atmosphere, this temperature, this water, this life, it's all temporary, beautiful precisely because it's fleeting. Let's leave this scorched world behind. Let's drift outward, back to the planet we know. The only one with oceans of liquid water, the only one with forests and life, the only one that is home. Let's return to Earth. Here we are, floating in the darkness of space, and there before us, hanging like a jewel against the infinite black, is Earth, home, the pale blue dot, the blue marble, Terra, Gaia, our world, the only one we've ever known, the only place in the entire universe where we know with absolute certainty that life exists. From this distance, Earth is breathtaking, Swirls of white clouds drift over blue oceans that cover 71% of the surface. The oceans, vast and deep, shimmering in the sunlight. So much water, water that makes everything possible. Continents peek through the clouds, green and brown, forests and deserts, mountains and plains. Antarctica glows brilliant white at the South Pole, a massive ice sheet covering an entire continent. The Arctic ice cap, smaller but still gleaming, surrounds the North Pole. The atmosphere, Earth's precious atmosphere, appears as a thin blue haze around the planet. From here, you can see how thin it really is, like the skin on an apple, a fragile envelope of gases, just 50 miles thick before space begins, protecting everything below. This atmosphere is everything. It provides the air we breathe. Nitrogen makes up 78%. Oxygen, the gas we need for every breath, makes up 21%. Argon, carbon dioxide, water vapor, and traces of other gases make up the rest. This mixture, this perfect balance, is maintained by life itself. The oxygen in our atmosphere wasn't always there. When Earth formed 4.54 billion years ago, there was no oxygen. The early atmosphere was carbon dioxide, nitrogen, water vapor, methane. Oxygen is reactive. It would have combined with rocks, with gases, disappearing quickly. But then life evolved photosynthesis. Tiny organisms in the oceans, cyanobacteria, learned to use sunlight to convert carbon dioxide and water into sugar, releasing oxygen as a waste product. For millions of years, this oxygen reacted with iron in the oceans, turning them rusty red, eventually precipitating out as iron oxide, creating the banded iron formations we mine today for steel. But gradually, after all the iron was oxidized, oxygen began building up in the atmosphere. This was actually poisonous to most life at the time. The Great Oxidation Event, about 2.4 billion years ago, was one of Earth's greatest extinction events, but it also opened the door for new, more complex forms of life. Life that could use oxygen for energy, life that could grow larger, more active, eventually, life like us. Earth's story begins 4.54 billion years ago. In the same rotating disk of gas and dust that formed the sun, the inner part of this disk, where Earth formed, was hot. Icy materials couldn't condense here. Only rock and metal. Small particles collided and stuck together. Pebbles became rocks. Rocks became boulders. Boulders became mountains, growing larger through countless collisions. Within about 10 million years, Earth had grown to roughly its current size. A ball of molten rock, glowing red hot. Its surface was a magma ocean. Temperatures of thousands of degrees. No crust yet, no oceans, no life. Just heat and slowly cooling. As Earth cooled, the heaviest materials sank toward the center. Iron and nickel, being dense, fell inward, forming the core. Lighter materials, silicon, oxygen, aluminum, floated toward the surface, beginning to form the first crust. The planet differentiated into layers. Today, Earth has a solid inner core of iron and nickel, about 1,500 miles in diameter. Temperatures here exceed 9,000 degrees Fahrenheit, hotter than the surface of the Sun. But the immense pressure keeps the iron solid. Surrounding this is a liquid outer core, iron and nickel flowing and churning, generating Earth's magnetic field through dynamo action. Above the core lies the mantle, nearly 2,000 miles thick, made of dense rock rich in iron and magnesium. The mantle is solid, but it can flow very slowly over millions of years, like an incredibly thick liquid. Convection in the mantle drives plate tectonics, moving continents, creating mountains, triggering earthquakes and volcanoes. Finally, the crust, the thin outermost layer where we live. Oceanic crust is just 3 to 6 miles thick. Continental crust, slightly lighter and thicker, averages about 25 miles. Thin as the skin on an apple compared to the 8,000-mile diameter of the entire planet. About 50 million years after Earth formed, something dramatic happened. A Mars-sized object, sometimes called Theia, struck Earth at an oblique angle. The impact was catastrophic. Both bodies were partially vaporized. Rock and metal were blasted into space. The heat was unimaginable. The debris from this collision went into orbit around Earth. Over time, perhaps just a few thousand years, this debris coalesced, pulled together by gravity, forming a new body, our moon. The moon is important, more important than you might think. Its gravity tugs on Earth, creating tides in the oceans. These tides mix nutrients, possibly playing a role in the origin of life. The moon's gravity also stabilizes Earth's axial tilt. Our planet is tilted 23.5 degrees, giving us seasons. Without the moon, this tilt would vary chaotically over millions of years, making climate unpredictable, possibly preventing complex life from developing. The moon is slowly drifting away, about 1.5 inches per year. As it does, it steals rotational energy from Earth. Our days are gradually getting longer. A day on Earth is now 24 hours. When the moon first formed, just after that massive collision, an Earth day was only about 5 hours long. Billions of years from now, if nothing else changes, Earth's day will be 50 hours, and the moon will hang motionless in the sky, locked in synchronous orbit. As Earth continued to cool after the formation, Water vapor in the atmosphere condensed. It began to rain, and it rained and rained, perhaps for millions of years, until the surface was cool enough for water to remain liquid. The first oceans formed. These early oceans were hot, acidic, lifeless, but they were there, covering much of the planet. And somewhere in these ancient seas, perhaps near volcanic vents on the sea floor, or in shallow tidal pools, or delivered by comets, the first life emerged. We don't know exactly when. We don't know exactly how. But by 3.8 billion years ago, perhaps earlier, life existed on Earth. Simple, single-celled, but alive, able to reproduce, to evolve, to change. For billions of years, life remained microscopic. Bacteria and archaea, slowly diversifying, developing new ways to extract energy from their environment. Some used chemicals, some learned to use sunlight. Evolution proceeded slowly, but relentlessly. Around 2.4 billion years ago, some bacteria evolved oxygen-producing photosynthesis. Cyanobacteria, blue-green algae, they use sunlight to split water molecules, combining hydrogen with carbon dioxide to make sugar, releasing oxygen. At first, this oxygen was absorbed by dissolved iron and rocks, but gradually it built up in the atmosphere, transforming Earth's air, making possible new forms of life, more complex life, life that could use oxygen for efficient energy production. About 600 million years ago, something remarkable happened. The Cambrian explosion. Suddenly, in geological terms, complex multicellular life appeared. Animals with bodies, with shells, with eyes. The oceans filled with strange and wonderful creatures, trilobites, Anomalocaris, the ancestors of everything that came after. Life moved to land. Plants greened the continents. Insects followed. Fish developed limbs and crawled ashore, becoming amphibians. Reptiles evolved. Dinosaurs ruled for 160 million years. Mammals waited in the shadows. 66 million years ago, an asteroid struck. The dinosaurs, except for birds, went extinct. Mammals diversified. Primates appeared. And eventually, in Africa, a few million years ago, our ancestors stood upright, began using tools, developed language, culture, art, science. We are so recent. Humans, modern humans, have existed for only about 300,000 years. Civilization, cities, and agriculture for only 10,000 years. We are newcomers, and yet we have transformed the planet. Earth's surface is constantly changing. The crust is broken into large tectonic plates. These plates float on the partially molten mantle below. They move slowly, a few inches per year, but over millions of years. This adds up. Plates collide. One slides beneath the other, subducting, melting, feeding volcanoes. Mountains rise where plates crunch together. India crashed into Asia, pushing up the Himalayas. Plates pull apart, creating new ocean floor where magma wells up. The Atlantic Ocean grows wider each year. The Pacific shrinks. The continents have moved enormously over Earth's history. Once they were joined in a supercontinent called Pangaea, about 200 million years ago. Pangaea began breaking apart. The pieces drifted. North America separated from Europe and Africa. South America split from Africa. India traveled north from Antarctica. Australia separated and moved northeast. The continents continue moving today. Africa is slowly splitting along the East African Rift. Someday, millions of years from now, Eastern Africa will break away, forming a new ocean. The Mediterranean Sea is closing as Africa moves north toward Europe. In 250 million years, the continents will come together again, forming a new supercontinent. The cycle continues. Earth has one natural satellite visible from our position, the Moon, orbiting at an average distance of 238,000 miles. From Earth, the Moon appears almost exactly the same size as the Sun, a cosmic coincidence that creates spectacular total solar eclipses. The Moon is tidally locked to Earth. It rotates once for each orbit, always showing us the same face. The far side, not dark, just never visible from Earth, remained unknown until spacecraft photographed it in 1959. From space, we can see Earth as it truly is, a living planet, the only one we know. Everything is connected. The oceans drive weather. Evaporation creates clouds. Clouds bring rain. Rain fills rivers. Rivers flow to the ocean. The cycle continues. Forests produce oxygen. Animals breathe that oxygen. Exhale carbon dioxide. Plants use that carbon dioxide. The cycle continues. This planet, our home, has given us everything. Every breath of air, every drop of water, every bit of food. We evolved here, adapted to its gravity, its atmosphere, its day length, its seasons. We are made of Earth's atoms, carbon from ancient plants, calcium from shells, iron from exploded stars. We are. The planet become conscious, looking back at itself. Let's think about what that means. The carbon in your DNA. Carbon that stores the genetic information making you uniquely you, was created inside a star. Not our sun, but an earlier star that lived and died before our solar system even existed. That star fused lighter elements in its core, creating carbon through nuclear fusion, building it atom by atom over millions of years. When that star reached the end of its life, it exploded, a supernova, one of the most violent events in the universe. The explosion was so powerful, so energetic, that it created elements heavier than iron, gold silver, uranium, elements that can't be made by normal fusion. They require the intense heat and pressure of a stellar explosion. That explosion scattered those elements, including your carbon, across space. The debris traveled for perhaps millions of years. Eventually, it encountered a giant molecular cloud. Our molecular cloud, the cloud that would collapse to form the sun and planets. Your atoms mixed with hydrogen and helium and dust. They were there when the sun ignited, when Earth coalesced from orbiting debris, when the first oceans formed. Some of your atoms might have been in those first oceans. Others might have been locked in rocks for billions of years. Some were definitely in living things before they became part of you, perhaps in ancient microbes, in trilobites swimming in Cambrian seas, in dinosaurs, in early mammals, in your ancestors. Your atoms have been recycled countless times. They've been in the ocean, in the air, in soil, in plants, in animals, in other humans. Nothing is new. Everything is borrowed, temporarily assembled into the form you call yourself, before being returned to the great cycle. In a very real sense, you've been here since the beginning. Not you as a conscious being, but you as matter, as atoms. Your substance is ancient, older than Earth, older than the sun, forged in stars, scattered by supernovae, gathered by gravity, organized by chemistry, animated by biology, made conscious by evolution. You are not separate from the universe. You are not in the universe. You are the universe. A temporary pattern of matter that has become aware of itself, looking out through human eyes at a cosmos that created those eyes, the universe experiencing itself subjectively. This is not metaphor. This is literal truth. The atoms reading these words, the neurons processing them, the consciousness understanding them, all made of stardust, all connected to everything, all part of one vast cosmic process that began nearly 14 billion years ago and continues right now, in this moment, in you. And Earth is not the center of the universe. It's not the center of the solar system. It's one planet among 8, orbiting an average star, in the outer regions of a galaxy, among billions of galaxies. We are small. Our time here is brief. But perhaps that makes it more precious. This blue marble, hanging in the darkness, is rare, perhaps unique, and it's ours to care for. Let's continue our journey outward from Earth to the 4th planet, the Red World, the planet that has fascinated humans for millennia. Mars, the god of war, glowing red in our night sky, beckoning us outward. The 4th planet, roughly half Earth's diameter, 1/10 Earth's mass, small but mighty in its hold on our imagination. As we approach, the first thing you notice is the color, red, rust, red, iron oxide red. The entire planet appears rust-colored because the surface rocks are rich in iron that has oxidized, rusted over billions of years. This is why Mars glows red when seen from Earth. The iron in its soil, the dust in its air. Mars is smaller than Earth, about half the diameter. If Earth were a basketball, Mars would be a tennis ball. Its mass is only about 10% of Earth's. If you stood on Mars, you would weigh about 38% of your Earth weight. You could jump nearly 3 times higher. The atmosphere here is thin, so thin. The pressure at the surface is less than 1% of Earth's, about 0.6% to be precise. And it's mostly carbon dioxide, 95% carbon dioxide, with small amounts of nitrogen and argon. You couldn't breathe it. The low pressure would be fatal even if the air were oxygen. Your blood would boil. The average temperature on Mars is -80 degrees Fahrenheit, 54 degrees below 0 Celsius. Cold, very cold. At the equator in summer, temperatures can reach a comfortable 70 degrees Fahrenheit in the afternoon. But at night, they plunge to -100 degrees or colder. At the poles in winter, temperatures drop to -200 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the air, creating seasonal polar caps of dry ice. But Mars wasn't always this cold and dry. The evidence is written everywhere across the surface. Valley networks that look like dried up river systems, outflow channels where massive floods once carved through the landscape, deltas where ancient rivers emptied into lakes, minerals that only form in the presence of liquid water. Mars, long ago, was wetter, warmer, more hospitable. Early Mars, perhaps 4 billion years ago, had a thicker atmosphere. Water flowed on its surface. It rained. Rivers carved valleys. Lakes filled impact craters. There may have been an ocean covering much of the northern hemisphere. The climate was not exactly Earth-like, but much more favorable than today. What happened? Why did Mars lose its water, its atmosphere, its warmth? The answer lies partly in its size. Smaller planets cool faster. Mars's core, once molten and churning, generating a magnetic field that protected the planet, gradually cooled and solidified. The magnetic field weakened, then disappeared. Without a protective magnetic field, the solar wind struck the atmosphere directly. Charged particles stripped away atoms and molecules. Gradually, over hundreds of millions of years, the atmosphere thinned, the pressure dropped. Water could no longer exist as liquid on the surface. It either froze or evaporated, lost to space, or locked underground as ice. Today, water still exists on Mars. The polar ice caps, clearly visible as bright white patches at the north and south poles, are made of water ice covered with seasonal layers of dry ice. Frozen carbon dioxide that condenses from the atmosphere in winter and sublimes back to gas in summer. Underground, radar from orbiting spacecraft has detected vast reserves of ice, buried glaciers, frozen lakes, more water than we initially imagined. And in certain locations, on steep slopes, dark streaks appear seasonally, recurring slope lineae, possibly caused by brief flows of very salty liquid water, briny enough to remain liquid at Martian temperatures. Though this remains debated, Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano that dwarfs anything on Earth. It rises 16 miles above the surrounding plains, 3 times taller than Mount Everest. Its base, 375 miles across, would cover most of Arizona. If you stood at its base and looked up, you couldn't see the summit. The mountain would extend beyond the horizon. Olympus Mons formed over billions of years. Lava welled up from the same hotspot repeatedly, building layer upon layer. On Earth, plate tectonics would move the crust, creating a chain of volcanoes like the Hawaiian Islands. But Mars has no plate tectonics. The hotspot stayed in one place. The volcano grew and grew, becoming a mountain larger than any in the solar system. Near Olympus Mons, the Tharsis Rise, a vast bulge in the crust supporting 3 more enormous volcanoes, Arsia Mons, Pavonis Mons, Ascraeus Mons, lined up like sentinels, each one larger than any volcano on Earth. This region, the size of North America, represents billions of years of volcanic activity, evidence that early Mars was geologically very active. On the opposite side of the planet, another extreme feature, Valles Marineris, the valley of the Mariner spacecraft that discovered it, the largest canyon system in the solar system, 2,500 miles long, 4 miles deep in places, 600 miles wide at its widest. It would stretch across the entire United States from coast to coast. It makes the Grand Canyon look tiny. Valles Marineris probably formed as the Tharsis region bulged upward. The crust stretched and fractured. Water may have carved some of the side channels. Landslides have widened it. But fundamentally, this is a tectonic feature, evidence that Mars, though smaller than Earth, experienced massive geological forces. The Martian surface is divided into 2 distinct regions. The northern hemisphere is mostly smooth lowlands, perhaps once the floor of an ancient ocean, young, relatively uncratered. The southern hemisphere is rugged highlands, heavily cratered, ancient terrain unchanged for billions of years. This dichotomy is one of Mars's great mysteries. Something resurfaced the north, perhaps a massive impact, perhaps volcanic flooding, perhaps the ocean itself, if it existed, deposited sediments. The answer remains unclear. Mars has 2 small moons, Phobos and Deimos, fear and panic, named after the attendants of the war god. These moons are tiny, irregularly shaped chunks of rock. Phobos is about 17 miles across, Deimos about 9 miles. They look like captured asteroids, dark, heavily cratered, orbiting close to Mars. Phobos orbits just 3,700 miles above Mars' surface. So close, it completes 3 orbits per day, racing across the Martian sky from west to east. It's gradually spiraling inward. In about 50 million years, it will either break apart, forming a ring, or crash into the planet. For decades, humans have sent spacecraft to explore Mars, more missions than to any other planet, orbiters mapping every square inch, landers analyzing soil, rovers driving across the surface, searching, always searching, for signs of past or present life. So far, we haven't found definitive evidence of life, but we found the ingredients, organic molecules, evidence of ancient habitable environments, lakes that persisted for millions of years, conditions where life could have emerged. Mars may have hosted life in the past, when it was warmer and wetter. Microbes might have thrived in ancient lakes, underground, where liquid water still exists. Life might survive today, sheltered from the harsh surface conditions. The search continues. Every rock analyzed by rovers on Mars, every soil sample, every atmospheric measurement is a piece of a puzzle. We're trying to understand what happened. When did Mars lose its atmosphere? How long did water flow? Were there lakes that lasted thousands of years, millions, long enough for life to emerge? Life on Earth appeared remarkably quickly. Once conditions were favorable, once liquid water existed, life emerged within perhaps a few 100 million years, maybe less. We don't know exactly when, because the earliest evidence has been destroyed by plate tectonics. But we know life was here at least 3.8 billion years ago, possibly earlier. If life appears that quickly when conditions are right, then Mars might have had life too, during its wet period, when rivers flowed and lakes filled craters, when the atmosphere was thicker and temperatures warmer. There was time, there was water, there were organic molecules delivered by asteroids and comets. All the ingredients were present. Maybe Martian microbes lived in those ancient lakes. Maybe they built stromatolites like early Earth bacteria did. Maybe they adapted as conditions worsened, retreating underground, following the water deeper as the surface dried. Maybe they're still there, dormant, waiting, frozen in the permafrost, or surviving in deep aquifers where liquid water still exists. Or maybe life never started on Mars. Maybe it almost did, but didn't quite. Maybe it did start, but didn't survive the transition as conditions worsened. Maybe Mars is a dead world and always has been. We don't know. Not yet. But the question matters. If we find life on Mars, even fossil microbes, it would be the most important discovery in human history. It would tell us that life isn't unique to Earth, that given the right conditions, life emerges, that the universe might be full of living worlds, that we're not alone. And even if we find no life, that tells us something too, that life is rare, precious, that Earth's biosphere is even more valuable than we thought. Either answer is profound. The dust on Mars is fine, very fine, electrostatically charged, clinging to everything. When the wind picks up, dust storms develop, sometimes small, localized, but sometimes they grow, engulfing regions. Occasionally, rarely, they grow to cover the entire planet. Global dust storms, lasting for months, darkening the skies, blocking out the sun, creating an eerie orange twilight even at noon. Despite the harsh conditions, Mars fascinates us. It's the most Earth-like planet in our solar system. A day on Mars, called a sol, lasts 24 hours and 37 minutes, almost the same as Earth's. Mars has seasons because its axis is tilted about 25 degrees, close to Earth's tilt. In winter, frost forms. In summer, temperatures moderate. Mars represents our future. Of all the planets, it's the one we might someday colonize. We could build habitats there, underground for radiation protection, use local resources, extract water from ice, produce oxygen from the atmosphere, grow food in greenhouses. It won't be easy, but it's possible. Perhaps one day, humans will walk on Mars, plant flags, build settlements, terraform the planet over centuries, thickening the atmosphere, warming the climate, perhaps restoring the water that once flowed, making Mars green again. But that's far in the future. For now, Mars remains a cold desert, a red world of ancient mysteries, evidence of a watery past, and perhaps, just perhaps, clues about life beyond Earth. Let's continue our journey outward, crossing a boundary, leaving the realm of rocky planets, entering the domain of giants. But first, we pass through a belt, a band of scattered debris, the asteroid belt. Between Mars and Jupiter, between the terrestrial planets and the gas giants, we pass through a region filled with rocks, the asteroid belt. Millions of objects, ranging from tiny pebbles to mountain-sized boulders, drifting through space, remnants of the solar system's formation. These are the asteroids, the minor planets, the pieces that never came together to form a world. Jupiter's massive gravity, stirring the region, prevented the material here from coalescing. Instead of a planet, we have millions of fragments, slowly orbiting the sun, each on its own path. The asteroid belt sounds crowded, millions of rocks, but space is vast. If you were standing on one asteroid, the next closest might be hundreds of thousands of miles away. You could travel through the asteroid belt and never see one. Most of the time, asteroids are separated by enormous distances, lonely rocks in the emptiness. The largest object here is Ceres, a dwarf planet, 590 miles across, nearly spherical, massive enough for its own gravity to pull it into a round shape. Ceres has a rocky core, a mantle of water ice, and possibly a subsurface ocean, liquid water beneath the frozen crust. Bright spots on its surface, deposits of salt left behind when water ice sublimated, glint in the sunlight. Other large asteroids include Vesta, Pallas, Hygeia, each with unique characteristics. Vesta has a massive crater at its south pole. From an impact so violent, it sent fragments to Earth as meteorites. Some asteroids are metallic, mostly iron and nickel, perhaps the exposed cores of larger bodies that broke apart long ago. Others are rocky, or icy, or mixtures. The asteroids follow elliptical orbits around the Sun, each on its own path, occasionally perturbed by Jupiter's gravity. Very rarely, asteroids collide, breaking into smaller pieces, slowly grinding each other down over billions of years. The asteroid belt is gradually eroding, but so slowly it will take trillions of years to disappear completely. This belt marks a boundary. Behind us lie the terrestrial planets, small, rocky, close to the Sun. Mercury, Venus, Earth, Mars. Worlds with solid surfaces you could stand on, warmed by the nearby Sun. Ahead lies the realm of giants, where hydrogen and helium dominate, where planets grow to enormous sizes, where temperatures plunge, where the Sun appears small and distant, where moons outnumber planets, where rings circle worlds. Let's cross this boundary now, leaving the asteroids behind, approaching the largest planet in our solar system, the king of worlds, Jupiter. There it is, growing larger with each moment. Jupiter, the fifth planet, the giant, the king. Jupiter is enormous, so large that 1,300 Earths could fit inside it. So massive that it contains 2.5 times the mass of all the other planets combined. If Jupiter were hollow, you could drop Earth inside and it would rattle around like a marble in a basketball. From a distance, Jupiter appears as a banded sphere, stripes of orange, brown, white, cream, running parallel to its equator. These bands are clouds, blown by fierce winds, organized into distinct zones by Jupiter's rapid rotation. The planet spins faster than any other, completing one rotation in just under 10 hours. A day on Jupiter is less than half an Earth day. This rapid rotation causes the planet to bulge at its equator. The centrifugal force pushes the equatorial regions outward. Jupiter's equatorial diameter is 89,000 miles. Its polar diameter is about 7,000 miles less. The planet is noticeably flattened, oblate. You can see the bulge. As we drift closer, the scale becomes overwhelming. Jupiter measures 89,000 miles across at its equator, 11 times wider than Earth. Despite its size, Jupiter has no solid surface to stand on. It's a gas giant, a world without ground. Beneath those beautiful clouds lies an atmosphere that extends down for thousands of miles, gradually becoming denser, hotter. The pressure builds, the temperature climbs, the gases compress. Eventually, perhaps 2,000 miles down, the hydrogen gas transitions into liquid hydrogen. There's no clear boundary, just a gradual change from gas to liquid. Deeper still, under pressures millions of times greater than Earth's atmosphere, hydrogen is compressed so tightly it behaves like a metal. Liquid metallic hydrogen, conducting electricity, generating Jupiter's powerful magnetic field through dynamo action. This exotic form of hydrogen exists nowhere on Earth, only in the crushing depths of gas giants. At the very center, there may be a solid core, rock and ice, perhaps 10 to 20 times Earth's mass, but no one knows for certain. The core is buried beneath 40,000 miles of hydrogen and helium, unreachable, hidden. Jupiter's atmosphere is turbulent, chaotic, beautiful. The light-colored bands, called zones, are regions where gas rises from the interior, cools, forms clouds of ammonia ice crystals at high altitudes. The dark bands, called belts, are regions where gas sinks, carrying darker compounds up from below, exposing deeper, warmer layers. Between these bands, winds scream at hundreds of miles per hour. Jupiter has the fastest sustained winds in the solar system, some reaching 400 miles per hour, constant, unceasing, driven by heat from the interior and the planet's rapid rotation. Lightning flashes in the clouds, bolts thousands of times more powerful than Earth's, illuminating the turbulent atmosphere in brief. Violent bursts. Thunder would be deafening if you could hear it, but there's no surface to stand on, no place to listen. And then there's the Great Red Spot, this massive storm, larger than Earth itself, has been raging for at least 350 years, possibly much longer. Early telescopes first observed it in the 1600s. It's been continuously monitored ever since. The Great Red Spot is a high-pressure anticyclone, an enormous storm rotating counterclockwise in Jupiter's southern hemisphere. Winds reach 270 miles per hour around its edge. The storm is so large, you could fit 2 or 3 Earths inside it. The color comes from complex organic molecules created by sunlight interacting with chemicals in the atmosphere. Perhaps red phosphorus brought up from deeper layers. Perhaps sulfur compounds. The exact chemistry remains uncertain, but the result is a deep reddish-orange hue that makes the spot unmistakable. The Great Red Spot appears to be slowly shrinking. Observations over the past century show it's gotten smaller. Once it was twice its current size. No one knows why. Perhaps it will eventually disappear, or perhaps it will persist for centuries more. Jupiter keeps its secrets, but the Great Red Spot isn't alone. Jupiter's atmosphere is filled with storms. Smaller spots, white ovals, brown barges, dotting the cloud bands. Some persist for decades. Others form and dissipate in months. The atmosphere is constantly changing, roiling, never still. Jupiter emits more heat than it receives from the Sun. The planet glows in infrared light, warm, radiating energy into space. Deep inside, Jupiter is still contracting, still slowly collapsing under its own gravity. This compression generates heat. The planet is cooling, but so slowly it will take trillions of years to cool completely. If Jupiter had been about 80 times more massive, if the cloud that formed it had contained just a bit more material, it might have ignited fusion in its core, become a star, making our solar system a binary star system. But Jupiter fell short, remaining a planet, though a magnificent one. Jupiter's magnetic field is immense, the strongest planetary magnetic field in the solar system, extending millions of miles into space, creating a magnetosphere that could contain the Sun. This magnetic field traps charged particles from the solar wind, forming intense radiation belts far more dangerous than Earth's Van Allen belts. These particles spiral along magnetic field lines, crashing into Jupiter's poles, creating auroras hundreds of times larger and more powerful than Earth's northern lights, glowing in ultraviolet and infrared. Visible from space as enormous ovals of light surrounding each pole. If you could see in ultraviolet, these auroras would be spectacular, pulsing, shimmering, dancing across the poles. But Jupiter's greatest treasures are its moons. Jupiter has at least 95 known moons, ranging from tiny captured asteroids just a few miles across to world-sized satellites larger than planets. The four largest, discovered by Galileo Galilei in 1610, are called the Galilean moons. These four worlds are so large you can see them with binoculars from Earth. Let's visit them, one by one. First, Io, the innermost Galilean moon. Io is the most volcanically active body in the solar system. As we approach, we see a surface painted in yellows, oranges, reds, blacks, sulfur compounds in various forms covering the landscape. The surface looks like a pizza or a rotten egg. Io orbits very close to Jupiter. The giant planet's gravity pulls and squeezes the moon as it moves through its slightly elliptical orbit. This constant flexing generates enormous heat through friction, tidal heating, melting Io's interior, driving hundreds of active volcanoes. Plumes of sulfur and sulfur dioxide shoot hundreds of miles into space, some reaching 200 miles high, forming temporary atmospheres that freeze and fall back to the surface when the eruptions stop. Lava flows hotter than anything on Earth, resurface the moon constantly, erasing impact craters almost as soon as they form. Io is young, its surface completely renewed every million years or so, constantly remade by volcanic fury. No other world in the solar system is so active. Io is a moon on fire. Next, Europa, the ice moon. Europa appears smooth from a distance, covered in water ice, reflecting Jupiter's light like a polished mirror. But as we get closer, we see the ice is cracked, scored with reddish-brown streaks, like veins running across the surface. These cracks formed as Europa's icy shell fractured and refroze, moved by tidal forces similar to those affecting Io. The ice shifts, cracks, refreezes, creating complex patterns. Some areas show chaotic terrain, blocks of ice that have broken apart and shifted before refreezing. But Europa's real story lies beneath the ice. Perhaps 10 to 15 miles down, there's likely a global ocean of liquid water, kept warm by tidal heating, possibly containing more water than all of Earth's oceans combined. This subsurface ocean makes Europa one of the most promising places to look for life beyond Earth. On Earth, life thrives near hydrothermal vents on the ocean floor, far from sunlight, deriving energy from chemicals rather than photosynthesis. Europa might have similar vents, places where heat from the rocky interior warms the water, creating habitable environments, possibly hosting alien microbes, life in a dark ocean, beneath miles of ice, on a moon of Jupiter, Ganymede, the third Galilean moon, the largest moon in the solar system, bigger even than the planet Mercury. Ganymede is unique. It has its own magnetic field, the only moon known to have one, generated by a liquid iron core deep inside. The surface is a mix of two types of terrain: dark, ancient regions, heavily cratered, billions of years old, and bright grooved terrain, where the icy crust has fractured and reformed, creating parallel ridges and valleys stretching for hundreds of miles. Like Europa, Ganymede probably has a subsurface ocean, buried beneath multiple layers of ice, perhaps 100 miles down. Another potential habitat for life, though less accessible than Europa's ocean. Finally, Callisto, the outermost Galilean moon. Callisto is heavily cratered, perhaps the most cratered object in the solar system. Its surface essentially unchanged for 4 billion years. No geological activity, no ice tectonics, just impact after impact, recorded in the ancient ice and rock. And yet, Callisto might also harbor a subsurface ocean. Magnetic field measurements suggest liquid water deep below, perhaps 200 miles down, making even this ancient battered moon potentially interesting for astrobiology. These 4 moons, Io, Europa, Ganymede, Callisto, are worlds in their own right. Each one tells a story. Each one holds mysteries. Together, they form a miniature solar system, orbiting Jupiter just as the planets orbit the Sun. Jupiter has protected Earth for billions of years. Its massive gravity acts like a cosmic vacuum cleaner, sweeping up asteroids and comets that might otherwise strike the inner planets. When a comet falls toward the inner solar system, Jupiter's gravity often captures it, pulls it off course, sends it somewhere else, away from Earth. This protection isn't perfect. Asteroids still hit Earth. The dinosaurs learned that 66 million years ago, when a 6-mile-wide asteroid struck what is now Mexico. But without Jupiter, impacts would be far more frequent. Complex life might never have time to evolve between catastrophic collisions. In 1994, humanity witnessed Jupiter's protective role firsthand. A comet called Shoemaker-Levy 9 had been captured by Jupiter's gravity, broken into fragments. The fragments, more than 20 pieces, crashed into Jupiter one after another over several days. Each impact released more energy than all nuclear weapons on Earth combined. Astronomers around the world watched. Telescopes trained on Jupiter captured images of the impacts. Dark scars appeared on Jupiter's cloud tops, each one larger than Earth. The impacts were violent, spectacular, terrifying, and we realized that could have been us. If that comet had been perturbed differently, if it had crossed Earth's orbit instead of Jupiter's, it could have ended civilization or all complex life. But Jupiter took the hit, as it has countless times before, as it will countless times again. The giant planet, our protector, standing between us and the dangers lurking in the outer solar system. Jupiter also gave us something else, a laboratory for understanding planetary atmospheres. The storms on Jupiter, the Great Red Spot, the wind patterns, all help us understand atmospheric dynamics, not just on gas giants, but on Earth too. The same physics applies, just at different scales. Weather prediction on Earth improved partly because of what we learned studying Jupiter. The mathematics of fluid dynamics, how heat drives circulation, how rotation creates bands of winds. These principles are universal. And Jupiter, being so large, so visible, so dramatic, is the perfect place to study them. The Galilean moons showed us that not all moons are dead rocks, that tidal heating can keep small worlds geologically active, that subsurface oceans might be common, that life might arise in places we never expected. Without Jupiter's moons, we might never have thought to look for life in subsurface oceans. Now they're some of our most promising targets. Jupiter is more than just a planet. It's a system, a miniature solar system, with its own dynamics, its own relationships, its own stories, and it's been there since the beginning, forming perhaps even before the Sun finished collapsing. shaping the solar system as we know it. Jupiter and its moons represent a system of incredible diversity, a giant planet that almost became a star, a volcanic moon constantly remaking itself, an ice moon with a hidden ocean, the largest moon in the solar system, an ancient world unchanged for eons, all bound together by gravity, dancing in the darkness. Let's move on now to the next giant, a world famous for its rings, the jewel of the solar system, Saturn. Approaching from Jupiter, we see it in the distance, a golden sphere surrounded by rings, glorious rings, impossibly thin rings that catch the sunlight and glow like a halo. Saturn, the sixth planet, the jewel. Saturn is the second largest planet, 9 times wider than Earth, though considerably less massive than Jupiter. While Jupiter is dense and compact for a gas giant, Saturn is fluffy. Its average density is less than water, 0.69 grams per cubic centimeter. If you could find an ocean large enough, Saturn would float. Like Jupiter, Saturn is composed mostly of hydrogen and helium, with traces of ammonia, methane, water. The atmosphere shows banded patterns, though more subtle than Jupiter's, clouds forming in horizontal stripes parallel to the equator. Saturn's rotation is almost as fast as Jupiter's, a day lasting just 10.5 hours. This rapid spin causes the planet to bulge prominently at the equator and flatten at the poles. Saturn is the most oblate planet in the solar system. The atmosphere displays occasional storms, though less frequently than Jupiter. But when storms do occur on Saturn, they can be spectacular. About once every 30 years, roughly once per Saturnian year, a massive storm erupts in the northern hemisphere, called a great white spot, spreading around the entire planet, then gradually fading over several months. Wind speeds on Saturn exceed 1,000 miles per hour near the equator, among the fastest in the solar system. These winds blow primarily eastward, in the same direction as the planet's rotation, creating jet streams in the atmosphere. At the North Pole, there's something extraordinary. A hexagonal cloud pattern, a 6-sided jet stream that rotates with the planet, each side about 9,000 miles long, with a massive hurricane at the center. This hexagon has persisted for decades, perhaps longer. Scientists believe the hexagon results from the interaction of different atmospheric layers moving at different speeds. The mathematics of fluid dynamics can create polygonal patterns under certain conditions, but seeing one so large, so persistent, on another planet is remarkable. But Saturn's atmosphere, as interesting as it is not why this planet captures our imagination. The rings, the magnificent rings, are what makes Saturn unforgettable. The rings extend outward from the planet for 175,000 miles, yet they're incredibly thin, in most places just 30 feet thick. Imagine something the width of a continent, but thinner than a 10-story building. If you made a scale model where the rings were as thin as a sheet of paper, they would be a mile wide. From a distance, the rings appear solid, a smooth disk of light. But as we get closer, we see they're actually composed of countless individual particles, ranging from tiny grains the size of sand to boulders the size of houses, each one orbiting Saturn independently, following its own path around the planet. These particles are mostly water ice, nearly pure, reflecting sunlight brilliantly. Mixed in are trace amounts of rock and organic compounds, giving some rings a slightly golden or reddish tint. The ice particles collide gently with each other, constantly redistributing, creating waves and patterns in the ring structure. The rings are divided into distinct bands, separated by gaps. The A ring, outermost of the main rings, separated from the B ring by the Cassini division, a gap 2,900 miles wide, visible even through small telescopes from Earth. The B ring is the brightest and most opaque, densely packed with particles. Inside that is the C ring, more transparent, allowing some of Saturn's light to shine through, like gauze. Beyond the main rings lie fainter rings, the D ring, closest to the planet. So tenuous, it's barely visible. The F ring, narrow and braided, held in place by two small shepherd moons that orbit on either side, their gravity confining the ring particles to a narrow path. The E ring, vast and diffuse, extending out to the orbit of Enceladus, one of Saturn's moons. This ring is constantly replenished by water ice erupting from Enceladus's surface. How did the rings form? Scientists aren't entirely certain. They may be the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces, pulled into pieces by the difference in gravitational pull on its near and far sides. Or they might be material left over from Saturn's formation, material that never coalesced into a moon. The rings are probably younger than Saturn itself. Some estimates suggest they're only a few 100 million years old, perhaps formed when dinosaurs walked on Earth. They're also temporary. The rings are slowly spiraling inward, raining down onto Saturn's upper atmosphere, losing an estimated 6 Olympic swimming pools worth of material per day. In another 100 million years, the rings may be gone, leaving future civilizations to wonder if they ever existed at all. But for now, the rings endure, magnificent, transient, beautiful. There's something melancholy about Saturn's rings. Their beauty is temporary. They've only existed for perhaps a few 100 million years. They'll only last another 100 million or so before disappearing, spiraling into Saturn, raining down onto the atmosphere, being absorbed by the planet that they once adorned. Future astronomers, billions of years from now, if anyone is around to observe, will see Saturn without rings, A naked gas giant like Jupiter, they might not even know rings ever existed unless they find our records, our images, our descriptions of how Saturn looked when we were here to see it. We are lucky to live in this brief window when Saturn has rings, lucky to have telescopes powerful enough to see them, lucky to have sent spacecraft like Cassini to study them up close, lucky to experience this cosmic artwork before it fades. Everything in the universe is temporary. Stars live and die. Galaxies evolve. Planets form and are eventually destroyed when their stars expand. Even black holes evaporate over inconceivable spans of time through Hawking radiation. Nothing lasts forever, but that temporariness is what makes things precious. If Saturn's rings lasted forever, would they be as beautiful? If we could see them anytime, would we appreciate them as much? Knowing they're fleeting, that we live in a special time, makes them more meaningful. The same is true of everything. Your life is temporary. The people you love are temporary. Earth's biosphere is temporary. Our sun is temporary. Everything is temporary. And that's okay. That's beautiful. Beauty doesn't need to be eternal to matter. A flower that blooms for one day is still beautiful. Perhaps more beautiful because of its brief existence. Saturn's rings remind us to appreciate what we have while we have it, to look up, to wonder, to feel grateful for the temporary beauty that surrounds us. Saturn has at least 146 known moons, more than any other planet. Most are small, irregular chunks of ice and rock, but several are substantial worlds. The largest is Triton, Saturn's crown jewel, the second largest moon in the solar system after Jupiter's Ganymede. Triton is unique. It's the only moon with a substantial atmosphere, thicker even than Earth's, composed mostly of nitrogen with some methane and traces of other hydrocarbons. This thick atmosphere is opaque, orange, hazy, obscuring the surface completely in visible light. But radar can penetrate the haze, revealing a world of surprising complexity. Triton has lakes, seas, rivers, all made not of water, but of liquid methane and ethane. These hydrocarbons, which are gases on Earth, are liquids in Triton's frigid environment. Temperatures hover around -290 degrees Fahrenheit, cold enough for methane to behave like water. The largest seas, Kraken Mare, Ligeia Mare, Punga Mare, are located near the North Pole. Bodies of liquid methane, larger than the Great Lakes, filled with liquid hydrocarbons hundreds of feet deep. Smaller lakes dot the landscape. Dry riverbeds carved by methane rain wind across the terrain. Triton has weather, methane rain, clouds form, drift across the sky. Occasionally unleash torrents of liquid methane that scour the surface, fill the lakes, then evaporate back into the atmosphere. Triton has a complete methane cycle, similar to Earth's water cycle. evaporation, condensation, precipitation, runoff. The surface beneath the clouds is a mix of water ice, as hard as rock in Titan's extreme cold, and organic compounds, complex carbon-based molecules called tholins, created by sunlight breaking apart methane in the upper atmosphere. These molecules rain down continuously, covering the surface in a layer of organic sludge. Titan might have a subsurface ocean too, liquid water mixed with ammonia, buried beneath the icy crust, warmed by radioactive decay in the rocky core. This makes Titan yet another candidate for life, though any life there would have to survive in extremely cold conditions, perhaps using liquid methane instead of water. Another fascinating moon is Enceladus, small, icy, reflective, one of the brightest objects in the solar system. Enceladus reflects nearly all the sunlight that hits it, its surface covered in fresh, clean water ice. At the South Pole, something remarkable is happening. Enormous geysers erupt from fractures in the ice, called tiger stripes, shooting water vapor, ice particles, and organic compounds hundreds of miles into space. These plumes are continuously active, fed by a subsurface ocean beneath the ice, kept liquid by tidal heating from Saturn's gravity. The plumes contain not just water, but also salts, silica particles, complex organic molecules, evidence that the ocean is in contact with a rocky core, creating conditions potentially suitable for life. Enceladus's ocean might have hydrothermal vents, similar to those on Earth's ocean floor. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through Enceladus's plumes, tasting the ocean directly, analyzing its composition. The data revealed all the basic ingredients for life as we know it: liquid water, organic compounds, and a source of chemical energy. Saturn and its rings and moons form a system of breathtaking beauty and scientific intrigue. The planet itself, with its banded clouds and polar hexagon, the rings impossibly thin, yet stretching across hundreds of thousands of miles. Titan, with its thick atmosphere and methane lakes. Enceladus, with its water plumes and hidden ocean. But we must continue our journey, moving ever outward, where the sun grows dimmer, where the cold deepens. Next, we encounter the ice giants, strange worlds tipped on their sides, colored pale blue-green. First among them, Uranus. Uranus, the seventh planet, nearly 2 billion miles from the Sun, a pale blue-green sphere floating in the darkness. Uranus is an ice giant, different from the gas giants Jupiter and Saturn. While those worlds are mostly hydrogen and helium, Uranus contains much more water, ammonia, methane, mixed with hydrogen and helium in smaller proportions. These ices, though they're not actually frozen solid in most of the interior, give Uranus its character. The planet is 4 times wider than Earth, large enough to fit 63 Earths inside, but with only about 15 times Earth's mass, less dense than the gas giants, more massive than the terrestrial planets, an in-between world. Below the outer atmosphere, there's likely a thick mantle of water, ammonia, and methane ices in various states, surrounding a small rocky core, perhaps the size of Earth. The atmosphere, what we can see, is remarkably bland. Unlike Jupiter's colorful bands or Saturn's occasional storms, Uranus appears almost featureless, a smooth pale blue-green disk with only the faintest hints of clouds or banding visible even in the best images. The color comes from methane in the upper atmosphere. Methane absorbs red light and reflects blue-green, giving Uranus its distinctive hue. The atmosphere is mostly hydrogen and helium, but that methane, even in small amounts, dominates the color. But Uranus's blandness hides something extraordinary. The planet is tipped on its side. While most planets spin roughly upright, with their axes perpendicular to their orbital plane, Uranus's axis is tilted 98 degrees, nearly horizontal. It essentially rolls around the Sun like a ball, rather than spinning like a top. This means Uranus has the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. During summer at the North Pole, the sun never sets, hanging in the sky day after day, year after year, for 42 years. Then autumn arrives, the sun sets, and winter brings 42 years of darkness, perpetual night, while the South Pole enjoys its long summer. What caused this bizarre tilt? The leading theory suggests Uranus was struck by a massive object early in its history, perhaps an Earth-sized body. That knocked it onto its side. This impact would have been catastrophic, possibly affecting the planet's internal structure, its magnetic field, its moons. Uranus's magnetic field is indeed strange. Unlike Earth, where the magnetic field aligns roughly with the rotation axis, Uranus's magnetic field is tilted 59 degrees from its axis and offset from the center, not aligned with the core. As the planet rotates, the magnetic field wobbles, creating a complex, asymmetric magnetosphere unlike any other in the solar system. The interior of Uranus is hot, reaching about 9,000 degrees Fahrenheit near the core. But unlike Jupiter and Saturn, Uranus emits very little heat. It radiates almost no more energy than it receives from the Sun, suggesting its interior is more static, less active, perhaps never fully mixed after its formation, or after the impact that tipped it over. Uranus has rings, faint rings, discovered in 1977 when the planet passed in front of a star. The star blinked on and off, revealing narrow rings blocking the starlight. These rings are dark, narrow, composed of very dark particles, possibly organic compounds mixed with ice. There are 13 known rings, each named with Greek letters or numbers, barely visible compared to Saturn's brilliant ring system. The planet has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Rather than mythological names like most other moons, Miranda, Ariel, Umbriel, Titania, Oberon, Puck, Ophelia, Cordelia. The 5 largest moons are all interesting. Miranda, the smallest and innermost, is particularly bizarre. Its surface is chaotically varied. Smooth plains sit next to jumbled, fractured terrain. Enormous cliffs rise from the icy surface. One feature, Verona Rupes, is the tallest known cliff in the solar system, a sheer drop of 6 miles. If you jumped off, in Miranda's low gravity, you would fall for about 10 minutes before hitting the bottom. Scientists aren't sure what created Miranda's strange terrain. Perhaps the moon was shattered by an impact and reassembled. Different pieces coming together in a jumbled configuration. Or perhaps tidal heating caused parts of the interior to melt and resurface, creating the varied landscape we see today. Uranus was discovered in 1781 by William Herschel, making it the first planet discovered with a telescope. The first discovered in recorded history. All the planets from Mercury to Saturn are visible to the naked eye, known since ancient times. Uranus required technology, observation, careful analysis to reveal its existence. Only one spacecraft has visited Uranus. Voyager 2 flew past in 1986, coming within 50,000 miles of the cloud tops. Taking the only close-up images we have, the encounter revealed the rings, discovered moons, measured the magnetic field, showed us just how bland the atmosphere appeared. But Uranus isn't always so featureless. Recent observations from powerful Earth-based telescopes have shown occasional storms, bright clouds appearing in the atmosphere, evidence that despite its calm appearance, Uranus has weather. These storms may be seasonal, becoming more common as the planet moves through its long, strange year. Wind speeds on Uranus can reach 560 miles per hour, racing around the planet in the same direction as its rotation. The winds are fastest near the equator, slower at the poles, creating zonal jets similar to those on Jupiter and Saturn, but much more difficult to observe due to the lack of visible cloud features. Deep in Uranus's interior, under immense pressure and temperature, some scientists believe carbon might be compressed into diamond rain, falling through the mantle, sinking toward the core, eventually forming a layer of diamond around the rocky center. This remains theoretical, but experiments have shown it's possible under the conditions present inside ice giants. Uranus is cold, very cold. with temperatures in the upper atmosphere dropping to minus 371 degrees Fahrenheit. It's the coldest planetary atmosphere in the solar system, even colder than Neptune despite being closer to the Sun. Why Uranus is so cold remains somewhat mysterious, possibly related to its lack of internal heat and the impact that tipped it over. From Uranus, the Sun appears tiny, about 400 times dimmer than it looks from Earth. Sunlight takes 2 hours and 40 minutes to travel from the Sun to Uranus, meaning when you see the Sun from this planet, you're seeing it as it was nearly 3 hours ago. Uranus drifts through its orbit slowly, taking 84 Earth years to complete one trip around the Sun. Anyone born on Uranus would wait a lifetime to see a single birthday. Uranus represents mystery, even after Voyager 2's flyby. Even after decades of observations from Earth-based telescopes, we still don't fully understand this planet. Why is it tipped over? Why does it emit so little heat? What created Miranda's bizarre terrain? Why is the magnetic field so oddly aligned? These questions remain unanswered, and there are no missions planned to return to Uranus anytime soon. No orbiters, no landers, no follow-up spacecraft. Voyager 2's brief encounter in 1986 remains our only close look. Those few hours of data collection, those precious images taken as the spacecraft raced past. Everything we know about Uranus comes from those brief hours and from patient observations through telescopes millions of miles away. It's not much. We're missing so much. But sometimes, not knowing is part of the beauty. Uranus holds its secrets. It's content to drift in its distant orbit, tipped on its side, experiencing its strange seasons, surrounded by its faint rings and small moons, mysterious, quiet, unbothered by our lack of attention. Perhaps someday, decades from now, we'll send another spacecraft. We'll orbit Uranus, study it for years, map its clouds, measure its interior, explore its moons, solve its mysteries. But until then, Uranus remains enigmatic, the sideways world, still waiting to tell us its full story. This pale-tipped, mysterious world is the penultimate stop on our journey. One more planet remains, the farthest from the Sun, the deep blue world discovered by mathematics before it was seen by eye. Let's continue to Neptune. Neptune, the eighth and final planet, nearly 3 billion miles from the Sun, the most distant world in our solar system. Neptune is similar to Uranus in size and composition. Another ice giant, 4 times Earth's diameter, with a mass 17 times greater. Deep blue in color, strikingly vibrant compared to Uranus's pale hue. Neptune appears as a gem, brilliant and mysterious, floating in the outer darkness. The deep blue color comes from methane in the atmosphere, but Neptune is more intensely blue than Uranus, despite having similar methane concentrations. Scientists believe there may be an unknown compound in Neptune's atmosphere, something that absorbs red light even more efficiently than methane, giving Neptune its richer color. The identity of this compound remains one of Neptune's mysteries. Neptune's atmosphere is active, turbulent, filled with the fastest winds in the solar system. Storms rage across the cloud tops, driven by internal heat, creating dramatic dark spots that appear and disappear over years. The most famous was the Great Dark Spot, discovered by Voyager 2 in 1989. This massive storm about the size of Earth raged in Neptune's southern hemisphere, with winds reaching 1,200 miles per hour around its perimeter. White cirrus, like clouds of methane ice, floated above the spot, casting shadows on the deeper cloud layers below. But when the Hubble Space Telescope looked at Neptune in 1994, the Great Dark Spot was gone. It had dissipated, vanished, replaced by other storms elsewhere on the planet. Neptune's atmosphere changes rapidly, storms forming and dissolving, cloud patterns shifting from year to year. These powerful winds are puzzling. Neptune receives less than half the sunlight Uranus does, yet it's far more active. The answer lies in internal heat. Neptune radiates about 2.6 times more energy than it receives from the Sun. Heat left over from its formation, still slowly leaking out from the interior. This heat drives convection in the atmosphere, creating the turbulent weather we observe. Like Uranus, Neptune's magnetic field is oddly tilted and offset from the center. The field is tipped 47 degrees from the rotation axis, suggesting that both ice giants generate their magnetic fields in a shell around the core, rather than at the center. Unlike the dynamos in Earth, Jupiter, and Saturn, Neptune has 14 known moons. The largest, Triton, is one of the most fascinating objects in the solar system. Triton is large, about the size of Pluto, with a diameter of 1,680 miles. Its surface is a frozen world, temperatures plunging to minus 391 degrees Fahrenheit, making it the coldest measured surface in the solar system. But Triton is not just cold, it's active. Voyager 2 discovered geysers erupting from Triton's surface, nitrogen gas and dark material blasting 5 miles into the thin atmosphere, then being carried downwind for over 60 miles before settling back to the surface. These cryovolcanic eruptions are driven by heat from the sun warming subsurface nitrogen ice, evidence that even in the outer solar system, worlds can be geologically active. Triton's surface is young. Few impact craters mark the icy terrain, suggesting the surface has been resurfaced relatively recently, perhaps within the last few million years. The landscape includes cantaloupe terrain, strange dimpled plains unlike anything seen elsewhere, smooth plains of frozen nitrogen, ridges and valleys, dark streaks left by the nitrogen geysers. What makes Triton truly unique is its orbit. Triton orbits Neptune backward, retrograde, opposite to the planet's rotation. This is the only large moon in the solar system to do so. Such an orbit strongly suggests Triton didn't form around Neptune, but was captured, probably from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit where Pluto resides. The capture would have been violent. Triton would have entered a highly elliptical orbit, swinging close to Neptune, then far away, experiencing extreme tidal forces. These forces heated Triton's interior, possibly melting it completely, destroying any record of its original surface. Over time, gravitational interactions with other moons, now long since ejected or destroyed, circularized Triton's orbit into the nearly circular path we see today. But Triton's story isn't over. The moon is slowly spiraling inward. Tidal forces are gradually pulling it closer to Neptune. In 10 to 100 million years, Triton will cross Neptune's Roche limit, the distance where tidal forces overcome the moon's gravity. When that happens, Triton will be torn apart, shredded into fragments, forming a spectacular ring system around Neptune, possibly more impressive than Saturn's. Neptune's other moons are small. The second largest, Proteus, is irregular, about 260 miles across, dark and cratered. Nereid, discovered in 1949, has the most eccentric orbit of any moon in the solar system, swinging from 850,000 miles away to nearly 6 million miles, suggesting it too might be a captured object. Neptune has rings, 5 main rings, along with several fainter arcs. The rings are dark, composed of very dark material, possibly organic compounds, barely visible even in the best images. The rings may be relatively young, perhaps created by impacts on Neptune's inner moons, grinding them down into dust. Neptune was discovered in 1846, but not by looking through a telescope first. Astronomers noticed that Uranus wasn't following its predicted orbit. Something was pulling on it, perturbing its path. Using mathematics, Urbain Le Verrier in France and John Couch Adams in England independently calculated where an unknown planet must be to cause these perturbations. When astronomers pointed their telescopes to that location, there it was, Neptune, a planet discovered by mathematics, by the power of Newton's laws, before it was seen by human eyes. This remains one of the great triumphs of theoretical astronomy, proof that the laws of physics could predict the existence of objects we'd never directly observed. This discovery was revolutionary. It proved that mathematics could reveal hidden truths about the universe, that human minds, sitting at desks with paper and ink, could predict the existence of objects never seen, that the laws of physics discovered on Earth applied everywhere, even billions of miles away, even to planets we didn't know existed. Neptune's discovery gave humanity confidence that we could understand the cosmos, that the universe operated according to laws we could discover and describe, that nothing was beyond the reach of human reason. This faith in mathematics and physics has driven exploration ever since. We calculate trajectories to send spacecraft to distant worlds. We predict where planets will be years in advance. We model stellar evolution and galaxy formation. We describe black holes and the expansion of the universe. All using mathematics, all based on the same principles that led us to Neptune. And we've been proven right again and again. Our predictions match observations. Our models describe reality. Mathematics, abstract human invention, turns out to be the language of the cosmos. The universe is comprehensible, and that is perhaps the greatest mystery of all. Why should the universe make sense to us? Why should the mathematics we invent in our minds correspond to physical reality? Why should the laws we discover on Earth apply everywhere? We don't know, but they do. And Neptune, discovered by mathematics before being seen by eyes, stands as proof. From Neptune, the Sun is just a bright star, 900 times dimmer than it appears from Earth. Sunlight takes over 4 hours to reach Neptune. Making real-time communication with spacecraft, they're essentially impossible. Commands must be sent well in advance. Responses take hours to return. Neptune takes 165 Earth years to complete one orbit. It has only just completed one full orbit since its discovery. Anyone born on Neptune would wait more than a human lifetime to celebrate a single birthday. Only Voyager 2 has visited Neptune, flying past in 1989, revealing a dynamic blue world, far more active than expected. The encounter lasted just a few hours, but the data returned revolutionized our understanding of ice giants, showing us that even at the edge of the solar system, worlds can be complex, active, beautiful. Neptune marks the boundary of the classical solar system. Beyond lie the Kuiper belt, the scattered disk, distant icy bodies that orbit in the outer darkness. But our journey tonight ends here, at Neptune, the farthest planet, the last stop before the void. But wait, there's one more world to visit. Small, distant, beloved, once called the 9th planet, now reclassified, but no less fascinating. Pluto. Pluto drifts in the Kuiper belt, beyond Neptune, in a realm of icy bodies left over from the solar system's formation. It's tiny, just 1,400 miles across, smaller than our moon, its surface a frozen mixture of nitrogen ice, methane frost, and reddish organic compounds. In 2015, after a journey of 9 years, the New Horizons spacecraft flew past Pluto, revealing a world far more complex than anyone expected. A giant heart-shaped region of smooth ice, Tombor Regio, mountains made of water ice, as hard as rock, in the extreme cold. A thin atmosphere that freezes and falls as snow when Pluto drifts farther from the Sun. Pluto reminds us that even the smallest worlds, the most distant, the overlooked, have stories to tell, have beauty, have mysteries. You don't need to be the largest, the brightest, to matter. Pluto matters, and so do you. Let's turn back now, look inward, and reflect on what we've seen. We've traveled far tonight, from the blazing heart of our solar system, the Sun, to the frozen outer reaches where Neptune drifts in eternal twilight. 8 planets, each one unique, each one a world unto itself. We passed Mercury, tiny and scorched, its cratered surface baking and freezing, a world of extremes holding ice in eternal shadows. We glided through Venus's sulfuric clouds, descending to a surface hot enough to melt lead, a greenhouse world gone wrong, a warning of what can happen when a planet loses its balance. We looked back at Earth, our home, the pale blue dot, the only world we know with life, with liquid water oceans, with forests and animals and humans who look up at the stars and wonder. Earth, rare, precious, fragile. We explored Mars, the red planet, once wet, now dry, holding secrets of ancient rivers and possible past life, beckoning us to visit, to explore, perhaps one day to stay. We crossed the asteroid belt, where failed planets drift, remnants of the solar system's violent youth, Ceres and Vesta and millions of smaller rocks orbiting forever in the space between worlds. We marveled at Jupiter, the king of planets, with its great red spot and powerful storms, protected by a magnetosphere large enough to swallow the Sun, surrounded by 4 world-sized moons, each fascinating in its own right. Io on fire, Europa with its hidden ocean, Ganymede the giant, Callisto the ancient. We gazed at Saturn, the jewel of the solar system, with rings so beautiful they take your breath away, impossibly thin, yet stretching across hundreds of thousands of miles, and Triton with its methane lakes, and Enceladus with water geysers erupting into space from a hidden ocean beneath the ice. We encountered Uranus, tipped on its side, pale and mysterious, experiencing seasons that last decades, a world knocked askew by ancient violence, rolling around the Sun like a ball. And finally, Neptune, deep blue, dynamic, the windiest world we know, with Triton slowly spiraling inward toward its eventual destruction. The farthest planet, the last outpost of our solar system, and little Pluto, beloved, complex, reminding us that even small worlds matter. What does it all mean? What do we take from this journey? Perhaps the first lesson is scale. The distances involved are almost incomprehensible. Light, traveling at 186,000 miles per second, takes 8 minutes to reach Earth from the Sun, but over 4 hours to reach Neptune. The solar system is vast, mostly empty space, with planets like islands in an ocean of darkness. And yet our solar system is tiny compared to the galaxy. All 8 planets, all the asteroids and comets, everything orbiting our sun, fits within a sphere about 6 billion miles across. The nearest star, Proxima Centauri, is 25 trillion miles away. If the solar system were the size of a quarter, the nearest star would be about 5 miles away. Our galaxy, the Milky Way, contains hundreds of billions of stars, each one potentially having its own system of planets. And there are hundreds of billions of galaxies in the observable universe. We are remarkably small, unimaginably small, and yet here we are, conscious, aware, able to contemplate our place in all of this. Perhaps the second lesson is uniqueness. Of all the worlds we visited tonight, only Earth supports life as we know it. Only Earth has liquid water oceans covering its surface. Only Earth has an atmosphere we can breathe. Only Earth, as far as we know, has looked back at the universe and understood what it's seeing. We might find life elsewhere, perhaps in the oceans of Europa or Enceladus, perhaps fossil microbes on ancient Mars, perhaps in the methane lakes of Triton. The search continues, but so far, Earth stands alone, a living world in a sea of barren ones. We are the universe become conscious. The atoms in your body, the carbon, the oxygen, the iron in your blood, were forged in the hearts of stars that exploded billions of years ago. Those stars scattered their elements across space, seeding the clouds from which new stars and planets formed. We are quite literally made of stardust. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. The universe, through us, has become aware. After 13.8 billion years of existence, some matter has arranged itself in such a way that it can think, wonder, ask questions, create art, write poems, build telescopes, explore other worlds, and yet consciousness is remarkable. Of all the ways matter can arrange itself, of all the possible configurations of atoms, some produce awareness, some produce understanding, some produce love and wonder and curiosity and joy. You are one of those configurations. Right now, in this moment, atoms arranged in such a way that they're aware of being atoms. Matter, contemplating matter. The universe examining itself. This is rare, probably very rare, on Earth. Consciousness took 4 billion years to evolve. 4 billion years of single-celled organisms before complex life appeared. Hundreds of millions more years before intelligence emerged. It's not easy. It's not inevitable. It might be extremely uncommon, which makes you precious. You, conscious, aware, thinking, are among the rarest things in the universe. You represent billions of years of evolution, countless generations of ancestors who survived long enough to reproduce, an unbroken chain stretching back to the first living cell. You are the universe become conscious, temporary, fragile, unlikely, and absolutely beautiful. And perhaps that's the third lesson. Connection. Everything is connected. The sun's light powers life on Earth. Jupiter's gravity protects us from comets that might otherwise strike our planet. The moon stabilizes our climate, making complex life possible. The death of ancient stars provided the materials to build planets, to build us. We are not separate from the cosmos. We are part of it, made of it, expressions of it. The future of space exploration is just beginning. Humans have walked on the moon. Robots have driven across Mars. We've flown past every planet, orbited Jupiter and Saturn, touched the sun's outer atmosphere, sent spacecraft beyond the solar system into interstellar space. But there's so much more to discover. Missions are planned to Europa, to search for life in its hidden ocean, to Triton to explore its methane seas, to Enceladus to taste its water plumes, to Mars again and again, seeking evidence of past or present life, preparing for human explorers. Perhaps in your lifetime, humans will walk on Mars, set foot on the red planet, plant flags, take samples, begin the long process of making Mars a second home. Perhaps we'll establish permanent bases, settlements that grow into colonies. The first step toward becoming a multi-planetary species. Perhaps we'll send missions to the outer solar system. Submarines to dive beneath Europa's ice. Boats to sail on Titan's methane lakes. Probes to sample Enceladus's geysers. Discovering what secrets these worlds hold. The solar system is our neighborhood. We're only beginning to explore it. Every mission reveals new mysteries, new questions, new wonders. The more we learn, the more we realize how much we don't know. Each answer raises 10 new questions. And beyond our solar system, there are other worlds. Thousands of exoplanets have been discovered orbiting other stars. Some are hot Jupiters, giant planets orbiting close to their suns. Some are super-Earths, rocky worlds larger than ours. Some orbit in the habitable zones of their stars, where liquid water could exist on their surfaces. Are we alone? Or is life common in the universe? Are there other civilizations out there, looking up at their stars, building their own telescopes, wondering the same questions we wonder? We don't know yet, but we're looking, listening, searching for signals, for signs of life beyond Earth. For now, we have our solar system, our sun, our 8 planets, our moons and asteroids and comets, our home. And what a home it is. Beautiful, diverse, full of wonders we're only beginning to understand. Take a moment to feel grateful. Grateful for this planet, this atmosphere, this water, this life. We exist in a universe that is mostly empty, mostly cold, mostly dark. And yet here on Earth, there is warmth, light, life, consciousness, love. You are made of atoms that were forged in stars. You are older than you know. The calcium in your bones came from exploding stars. The iron in your blood, the oxygen you breathe, all of it created in stellar furnaces, scattered across space, eventually finding its way here, becoming you. You are a child of the cosmos, a way for the universe to experience itself, to know wonder, to feel awe, to love and be loved. And so our journey comes to an end. We've drifted through the solar system, visiting each world, seeing the variety and beauty that surrounds us, from the sun-baked surface of Mercury to the icy geysers of Enceladus, from the great red spot of Jupiter to the rings of Saturn, from our precious Earth to distant Neptune at the edge of darkness. Let these wonders drift into memory now, like dust settling through space, coming to rest in the quiet corners of your mind. There's nothing more you need to understand tonight, nothing more to remember, just the peaceful feeling of having traveled far and returned safely. Your body is heavy now, relaxed, supported by whatever surface you're shown. You're resting on. Your breathing is slow, steady, peaceful, each breath carrying you deeper into rest. Let yourself drift, like a spacecraft floating gently through the darkness. No destination, no urgency, just floating, peaceful. The planets continue their ancient dance. Mercury racing around the sun, Venus shining bright in Earth's sky, Mars glowing red, Jupiter and Saturn majestic in the outer system, Uranus and Neptune in their distant orbits, all of them moving through space, following paths they followed for billions of years, paths they'll follow for billions more. And Earth, our beautiful Earth, continues spinning, day turning to night, night turning to day, the seasons changing, the tides rising and falling, life continuing in all its magnificent diversity, all of it, all of us, together on this pale blue dot, floating in the vastness. If you've enjoyed this journey, if you've found peace in these words, perhaps consider liking this video, subscribing to Calming Cosmos for more peaceful explorations of our universe, leaving a comment about which planet fascinated you most. But there's no pressure, nothing you must do. Just rest. Share this with someone who loves space, or someone who struggles to sleep, or someone who simply needs a moment of peace in their day. Or don't. That's okay too. Thank you for traveling with us tonight. Thank you for exploring the solar system, for wondering about our place in the cosmos, for seeking peace under the stars, for taking this time for yourself. Sleep well. Dream of distant worlds, of ringed planets and hidden oceans, of volcanic moons and ancient craters, of possibilities yet undiscovered. Remember that you are part of something vast and beautiful. You are connected to everything, to every star, every planet, every atom in the universe. You are not separate. You are woven into the fabric of existence. You are stardust. You are ancient. You are temporary. You are eternal. You are small. You are infinite. You are made of the same material as stars and galaxies. You are a conscious part of a conscious universe. Rest now. Let go of everything. The day is done. Tomorrow will come. But for now, there is only this moment, this breath, this peace. We are all made of stars, every single one of us, forged in cosmic furnaces, scattered across the void, eventually finding our way here, to this planet, this moment, this life. Sleep well, traveler. Rest in the knowledge that you are exactly where you need to be, that you are part of something beautiful, something vast, something mysterious and wonderful. The universe continues its eternal dance. Stars are born and die. Galaxies spin. Planets orbit. And you are here, breathing, existing, being. That is enough. You are enough. Good night, explorer. May your dreams be peaceful. May you wake refreshed. May you carry with you always the knowledge that you are made of stars. We are all made of stars. Rest well. Good night.